You were sitting in gridlock, right? Just staring at this massive, seemingly dormant dirt pit surrounded by chain link fences.
Yeah, we've all been there.
Exactly. And it's the site of a new subway extension, or maybe a highway overpass. You look at the fade-in project board, and the completion date reads something completely absurd like 2035.
And you just sort of sigh and accept it.
Right. The frustration is universal because, think about it, we live in an era where global financial markets execute billions of trades in microseconds.
Oh, absolutely.
And artificial intelligence generates these wildly complex software architectures in seconds. Yet, the physical reality around us, like pouring concrete, laying steel, digging tunnels, it just seems permanently tethered to the operational speeds of the 19th century.
It really does. It's like we're stuck in the past when it comes to the physical world.
Yeah. We've just accepted this immense friction as like an unchangeable law of the universe.
Which is actually the defining paradox of modern infrastructure. I mean, we operate with this massive cognitive dissonance.
What do you mean?
Well, we just assume that because a suspension bridge or, say, a hyperscale data center is physically heavy, its timeline just naturally has to stretch across a decade. We blame the sheer mass of the materials.
Right, because heavy things take a long time to move. It feels intuitive.
Exactly. But as we pivot into this new era driven by unprecedented infrastructural demands...
Like the AI boom, right?
Yeah, exactly.
Yeah.
From gigawatt-scale clean energy facilities to the sprawling semiconductor fabs powering the AI revolution, a society's ultimate competitive advantage is no longer merely capital.
So it's not just about who has the most money anymore.
No, not at all. The dominant currency is time, the capacity to translate a digital blueprint into physical reality without systemic latency. Well, that is what will dictate global leadership.
And that is exactly the core mission of our deep dive today.
Okay.
We are pulling apart the mechanics of a radical paradigm shift laid out in Paramendra Kumar Bhagat's expansive manuscript. It's called The Speed Builders, How Humanity Can Deliver Mega Projects in Months, Not Decades.
It's a fascinating read.
It really is.
Yeah.
And we're pairing it with a dense supplementary infographic titled Building the Future Faster. Together, this source material dismantles the illusion that construction speed is constrained by physics.
Right. It completely flips the script.
Yeah, because they argue the true bottleneck is human organizational architecture. Our goal today is to decode this blueprint for building civilization, like 10 times faster.
And Fagat isolates the precise failure points really well. When most people conceptualize a project delay, they visualize a mechanical failure on site,
Like a crane breaking down or something.
Exactly. Or a concrete pour halted by an unseasonal storm. But the actual physical manipulation of matter, the lifting, pouring, and welding, that represents a remarkably negligible fraction of a mega project's total life cycle.
Which is wild to think about. The hidden delays are entirely informational. We're dealing with an approval cascade.
Oh, massive approval cascade.
Right. So the heavy lifting isn't the steel, it's the permitting, the convoluted financing tranches, the procurement delays, and the regulatory coordination.
It's a paperwork problem, basically.
Yeah, exactly. It's like thinking a slow computer is caused by the monitor, when really the CPU is just waiting on data. The physical actuators, the machines, are just sitting idle, waiting for the informational go-ahead.
That's a really great analogy.
But wait, let's pause and ground this in physical reality for a second, because concrete still has a specific curing curve governed by exothermic chemical reactions.
True. You can't cheat chemistry.
Right. And structural steel has a maximum tensile load and requires specific logistical handling. Like, we can't simply wish away the laws of thermodynamics and gravity, so how much can we really speed up the physical reality?
Well, what's fascinating here is that, yes, physics sets an absolute floor on speed, certainly. The chemical curing time of Portland cement is a hard constraint.
Okay, so we agree on that.
But Bagat's analysis reveals that our current deployment systems operate vastly below those physical limits. The physical constraints are almost never the active bottleneck.
Wait, really? So we aren't even coming close to the physical speed limit?
Not even close. He introduces this concept that every infrastructure initiative is simultaneously two distinct projects. There is the visible execution.
The deployment of equipment, labor, dirt, all that.
Exactly. But running parallel to that is the invisible architecture. The contractual obligations, the design iterations, the compliance verification, and the risk management protocols.
The invisible data layer.
Right. And currently, that invisible data layer is incredibly bloated, largely because of what the text defines as the sequential mindset.
Okay, the sequential mindset.
Yeah.
We treat infrastructure like a linear relay race.
That's the perfect way to visualize it.
Yeah, the planners hold the baton until the conceptual phase is entirely exhausted, and only then do they hand it to the design engineering teams.
Who then lock in every single schematic before passing it to the permitting authorities.
Right, and only after the bureaucratic rubber stamp is finally acquired does procurement begin sourcing the long lead materials.
And while that single baton is moving, the rest of the capital and labor is completely immobilized, just waiting.
Wow. So if you look at the sources breakdown of the hidden anatomy of a mega project,
You see financing idling while design finalizes.
yeah, and procurement is tethered to the closing of the financing rounds. It is this endless end-to-end chain of synchronous dependencies.
Exactly. If a project has 12 distinct phases and each requires a year of linear progression, the math dictates a 12-year timeline.
So if the problem is this relay race sequence, the solution just has to be running all the races at the exact same time, which causally leads directly into the concept of parallel execution, right?
Yes, exactly. Which brings us to Chapter 3, The Death of Sequential Thinking.
I love that title, The Death of Sequential Thinking.
It's bold. And to see it in action, we have to look at the sectors where a 12-year timeline is basically a death sentence.
Okay, which sectors are those?
The hyperscale data center operators and the semiconductor fabrication industry.
Oh, right, because technology moves too fast.
Exactly. The capital expenditure in those sectors is so immense and the technology life cycle is so brief that waiting even 3 years for a facility guarantees you are deploying obsolete hardware on day one.
That makes total sense.
Right.
They literally cannot afford the relay race.
No, they can't. Consequently, they've transitioned from a traditional waterfall methodology to concurrent engineering.
Concurrent engineering. Okay, break that down for us.
The fundamental pivot is moving away from the demand for perfect information and instead operating on actionable information.
Actionable information. So it means initiating immense physical operations before the granular details of the downstream systems are even resolved.
Precisely. The manuscript refers to this as rolling design releases.
Rolling design. Okay, let's unpack this. To translate that from the engineering jargon, it means you begin mass earth-moving and foundation piling based purely on the macrostructural footprint.
Yes. While the
Mechanical, electrical, and plumbing routing.
Right, while all of that is still actively being modeled in the digital environment.
Wow. So you're pouring the foundation before you even know where the air conditioning goes.
Basically, yes. A traditional risk manager would view that as terrifying.
I mean, it sounds terrifying. Pouring a foundation without finalizing the load distributions of the roof-mounted HVAC systems seems incredibly reckless.
It does seem that way. But in these industries, the risk of delay heavily outweighs the risk of rework. Concurrent execution turns a linear timeline into a multi-threaded network of operations.
Okay, let's unpack this with an analogy. It's like a massively multiplayer online game. Right?
Yeah, I like where this is going.
Think about it. Thousands of players interact simultaneously in the exact same environment without waiting for the person next to them to finish their quest.
Right, the world doesn't pause for one player.
Exactly. Instead of a single player playing a linear storyline where event B can't happen until event A is done, everyone is doing everything at once.
That is a highly accurate parallel. And to prevent that multi-threaded physical execution from collapsing into cascading interference...
Because obviously in the real world, you don't want people literally tripping over each other.
Exactly. To prevent that, the fastest builders adhere to strict operational axioms. Vagot categorizes these as the 7 laws of fast infrastructure.
The 7 laws. Let's dig into a few of those.
Well, the foundational law is the relentless standardization of anything that does not generate a competitive advantage.
Standardize everything.
Yeah.
So if the specific layout of a medium voltage electrical room doesn't give your data center a competitive edge in processing latency or thermal efficiency.
You do not commission a bespoke design for it. You stamp out the exact same schematic you used on your last 10 facilities.
Because every custom element introduces friction.
Customization demands unique engineering review, anomalous procurement chains, and specialized labor training. It's a massive drag on speed.
So by stripping away that non-strategic customization, organizations achieve the second law, right? Building once to learn forever.
Exactly. They convert isolated capital projects into an iterative learning system.
Meaning the supply chain anticipates the standardized components, The labor force develops muscle memory for the assembly sequencing.
And the velocity just compounds with every iteration. It's a snowball effect.
But wait, executing in parallel requires immense standardization.
Yeah.
You can't start building a foundation early if the building is entirely custom.
No, you can't.
And pushing concurrent execution to its absolute limit, running procurement, design, and foundational construction simultaneously that requires a level of predictability that a muddy, weather-exposed dirt lot simply cannot provide.
That's the crux of the issue right there.
Right, because if procurement isn't just reacting to design, but actively shaping it based on real-time global supply chain availability, the assembly process has to be perfectly controlled.
You can't execute a multi-threaded process if a local rainstorm throws off your entire critical path.
So this necessitates moving construction off the muddy, unpredictable site into a controlled environment.
Yes, which leads perfectly into Chapter 4. The factory eats construction.
I love that visual. The factory eats construction.
It's exactly what's happening. Construction is rapidly merging with manufacturing. We're seeing buildings become products.
Right, because the historical separation where manufacturing utilized controlled indoor environments for mass production, while construction fought the variables of climate and geography outdoors, that whole division is dissolving.
It has to dissolve. Factory environments eliminate weather delays, they stabilize supply chains.
And they compound that learning through repetition we just talked about.
Exactly. The modern megaproject site is shifting from a place of fabrication to a pure assembly matrix.
Assembly matrix. So we're talking about plug-and-play infrastructure and containerized facilities.
Yes, the construction site is no longer where you make things. It is purely a place of assembly. You just click the pieces together.
Which honestly sounds like we're just clicking together giant Lego bricks.
It's a very similar concept, yes.
But let me push back on this a bit. Because if everything is standardized, do we lose the art of architecture?
Ah, the aesthetic question.
Yeah. Are we doomed to live in identical, boring, cookie-cutter cities? Because if every building is just a factory-stamped Lego set, that sounds incredibly dystopian.
It's a very valid concern. The tension between standardization and architectural identity is significant. But Vagat clarifies a critical distinction here.
Okay, what's the distinction?
Standardization happens at the interface and module level, not necessarily at the aesthetic level. Complexity is packaged, not eliminated.
Packaged complexity. How does that work in practice?
Look at how automotive manufacturing evolved with shared platform architectures. A single modular chassis and powertrain system can underpin a rugged utility vehicle, a luxury sedan, and a high-performance sports car.
Oh, that makes sense. The bones are the same, but the skin is different.
Exactly. The underlying complexity is packaged and standardized to achieve massive economies of scale and assembly speed. But the outward configuration and user experience remain highly customized.
Okay, I see. So the structural grid, the elevator cores, and the MEP distribution nodes, those become the standardized chassis.
Precisely that. The complexity is front-loaded in the factory. The source material highlights the evolution of healthcare infrastructure as the prime example of this.
Hospitals. Yeah, those take forever to build.
Historically, yes. Acute care hospitals are notoriously slow because patient rooms require incredibly dense, heavily regulated integrations.
You've got medical gases, redundant power, data systems, specialized HVAC.
It's a nightmare to coordinate on a dusty construction site. So the modern approach strips that fabrication out of the building site completely.
Wow. So they build the rooms off-site.
Entire patient wings are being fabricated as volumetric modules.
Wait, really? The whole wing?
The whole room. The factory handles the drywall, the antimicrobial finishes, the lighting arrays, even the hydrostatic testing of the medical gas lines.
So it's fully finished before it even leaves the factory?
Completely.
Yeah.
The room is sealed, shipped on a specialized flatbed, craned into the structural frame, and physically coupled to the building's central arteries via standardized quick connect interfaces.
Like plugging a USB drive into a computer.
Exactly. The Building the Future, faster infographic, visualizes this transition beautifully under its factory-first construction section.
Yeah, I'm looking at that part now. It says, everything possible is built in factories with robotic precision.
The mandate is clear. The site itself merely coordinates the integration.
But coordinating that integration, coordinating thousands of off-site factories, shipping modular parts to a single assembly site, that requires a brain that can handle millions of variables at once.
Oh, absolutely.
Because if you are operating a traditional sequential site, your materials arrive roughly when the schedule dictates, and you manage the buffer locally.
Right. You just pile it up on site.
But if you transition to an assembly matrix, relying on 50 distinct manufacturing facilities across a continent, each producing highly specialized volumetric modules, structural steel assemblies, and prefabricated electrical skids.
And you are running this on an accelerated, multi-threaded timeline.
Exactly. The sheer volume of variables is far beyond human capacity. A slight delay in rail freight out of a module factory could misalign the crane scheduling for an entire week, rippling through the critical path.
The human mind cannot simultaneously calculate the systemic impact of 1,000 moving variables across a global supply chain. It's just not biologically possible.
Which brings us to Theme 4, tapping into Chapter 5, AI Project Managers and the infographics AI orchestration layer.
This is where things get truly sci-fi, but it's happening right now.
We need to dig into the mechanics of that orchestration because this goes far beyond standard project management software, right?
Way beyond. A traditional master schedule is a static, reactive document. It breaks the moment it encounters reality.
Right. A delay happens, the telemetry eventually filters up to the project management office.
Human analysts hold coordination meetings to assess the impact, and the master schedule is manually rebaselined.
And the latency in that response cycle is catastrophic for a concurrent execution model.
Exactly. The AI orchestration layer Bhagat describes operates on continuous, real-time schedule optimization and risk prediction.
Meaning it handles millions of variables simultaneously. It is constantly ingesting macro and micro data sets.
It isn't just looking at the site telemetry. It's parsing global atmospheric pressure models to predict a typhoon in the South Pacific.
Wait, really? It looks at global weather.
Yes, and it cross-references that weather anomaly with the geolocations of cargo vessels carrying specific long-lead materials for the project.
So the AI spots a storm in the Pacific and instantly recalculates the concrete pour schedule in Texas.
Exactly. And when it calculates the probabilistic delay of those vessels, it doesn't wait to alert a human manager to convene a meeting.
It just acts on it.
The AI instantly runs a Monte Carlo simulation across millions of alternative scheduling permutations, identifies the new mathematically optimal critical path, and autonomously reallocates site labor and machinery to different zones to maintain velocity.
All while the materials are delayed. That is mind-blowing.
And if we connect this to the bigger picture, that real-time reallocation relies entirely on what Bhagat calls the living digital twin.
The living digital twin. Okay, explain that.
Because the AI isn't just managing a spreadsheet. It's interfacing with a high-fidelity, dimensionally accurate simulation of the project that updates in real time. The project exists simultaneously in the digital and physical worlds.
So as every steel beam is torqued into place and every prefabricated module is locked in, the digital state mirrors the physical state perfectly.
Perfectly, the implications of that perfect synchronization are profound.
Listeners, just imagine this. Imagine the project effectively rehearsing itself thousands of times before a single shovel hits the dirt.
That's exactly what's happening. The AI introduces synthetic chaos into the twin, simulating catastrophic supply chain failures, severe weather events, or labor shortages, and develops optimized recovery protocols.
So by the time the physical site encounters a disruption, the orchestration layer has already executed the solution synthetically.
It's anticipatory rather than reactive.
The infographic details this so well, showing how digital twins simulate everything to test thousands of scenarios.
And how AI project managers make millions of decisions in real time.
But, this digital brain is incredible. But eventually, software has to interact with dirt, steel, and gravity.
It can't stay in the cloud forever.
Right. The AI has to leave the screen and enter the machine. Which brings us to Chapter 6, the rise of physical AI, and Chapter 7, building with swarms.
The muscle and the swarm, we're talking about AI becoming physical.
Because historically, mechanization in construction has focused entirely on amplifying human strength, right? Like a bulldozer.
Exactly. Hydraulic excavators and tower cranes allowed a single human to exert the force of 1,000 laborers. But the cognitive burden...
The spatial judgment, the sequence of operations.
Right. The real-time adjustments to material variances, all of that remained entirely dependent on the human operator in the cab.
But physical AI shifts the paradigm. We're moving from machines that amplify human strength to machines that amplify human judgment.
That's the key distinction. An autonomous excavator operating today isn't just executing pre-programmed macros.
It's not just a remote-controlled car.
No, it has the 3D topological data of the digital twin loaded directly into its local compute module. It utilizes LiDAR, radar, and inertial measurement units.
To read the soil density and dynamically adjust its hydraulic pressure.
Exactly, to achieve the exact subgrade required without over-excavating. It knows the target grade via GPS.
And this transition eliminates the biological constraints of the labor force. I mean, we're talking about the true 24/7 construction site.
Machines don't sleep.
They don't need shift changes. They don't suffer from fatigue-induced error rates.
And because they navigate via multispectral sensor arrays, they operate at peak efficiency in complete darkness.
Okay, so what does this all mean? Are we talking about giant transformers?
Not quite transformers, but it is a massive leap forward.
But let me push back again. Because a site operating continuously without human presence sounds incredibly efficient, but also highly volatile. Well, if we are scaling this up to swarm intelligence, we aren't talking about a single autonomous bulldozer. We're talking about maybe a swarm of 100,000 robots.
Yes, building in parallel.
But how does a swarm of 100,000 robots not just crash into each other? Human sites have strict hierarchies for safety.
They do. And the natural assumption is that a centralized supercomputer acts as a puppeteer, sending distinct joystick commands to every single robot over a network.
Right, like an air traffic controller.
But that architecture is inherently fragile. The bandwidth requirements are immense, and even milliseconds of network latency could result in massive physical collisions.
So how do they coordinate?
Fagat points out that the solution relies on decentralized coordination, specifically swarm intelligence derived from biological models. Nature solved mega projects millions of years ago.
Like ants and bees.
Exactly. A termite mound is a complex, thermally regulated architectural structure built by millions of independent agents without a centralized architect.
Wait, really? There's no head termite directing traffic?
No. The intelligence is distributed. It's embedded in the local interactions, not a master blueprint.
So there is no central foreman.
Right. In the context of a robotic construction swarm, the AI orchestration layer does not micromanage the pathing. It establishes the global objective, for instance, excavate this sector to this specific grade, and sets the operational constraints.
And the individual autonomous units make local decisions based on real-time sensor data.
Yes. They act as edge computing nodes. They communicate via short-range mesh networks with the units immediately adjacent to them.
So much like how a school of fish moves without a leader.
Precisely. If an autonomous dump truck detects an unexpected geotechnical anomaly, like a massive subterranean boulder,
It doesn't query the cloud for permission to divert.
no. It instantly calculates a local bypass route, broadcasts that spatial constraint to the local mesh, and the rest of the swarm fluidly adjusts its pathing algorithms to accommodate the new obstacle.
It's incredibly resilient.
Yeah.
A localized mechanical failure in one unit doesn't stall a central sequence. The swarm just roots around the dead node.
The infographic depicts this swarm construction really well, showing thousands of robots building in parallel.
But here's a thought. 100,000 robots working 24/7 will consume materials at a terrifying rate.
Oh, the burn rate is astronomical.
Right. If a single part is missing, the swarm starves. This requires a completely new kind of supply chain.
Which is Chapter 8, Autonomous Supply Chains. Because you're right, that starvation risk necessitates a fundamental rewiring of global logistics.
Delays often originate thousands of miles away from the site.
Exactly. You cannot feed a hyper-efficient, continuously operating swarm using legacy purchasing methodologies. Fagat introduces the concept of predictive logistics.
Predictive logistics.
Yeah.
Breaking down the shift from reactive purchasing to predicting the future, basically.
Essentially, yes. AI systems forecast disruptions before they happen by analyzing global data weather, labor markets, geopolitics.
And this leads to the self-healing supply chain.
Yes. It operates very much like a biological immune system.
I love this analogy. Let's explore that. The self-healing supply chain is like the human immune system. It detects a threat, like a delayed shipment, and automatically sends white blood cells or alternative suppliers to fix the problem before the body even feels sick.
That is a perfect way to explain it. The predictive algorithms are continuously mapping the global supply network. If it detects a sudden spike in geopolitical instability near a critical maritime choke point,
Or a localized power grid failure at a primary steel fabrication facility.
it identifies the impending material deficit weeks before it impacts the construction site. And crucially, it executes the mitigation autonomously.
Without human intervention, it doesn't draft a memo for a procurement team to review.
No. If a supplier fails, the system instantly finds alternatives, books autonomous shipping, and reroutes materials.
Using smart contracts on a verified blockchain, right? To
Right.
ensure total component visibility.
Yes, the manuscript details a great example of tracking a steel beam from inception.
Let's trace that. The digital twin of that beam is created the moment the iron ore is extracted from the ground.
Exactly. The telemetry tracks the exact metallurgical composition during forging
Then the thermal stress tests in the smart factory,
onto an autonomous cargo ship.
right to the robotic crane that installs it.
The physical object and its verified digital history are permanently fused.
It's mind-blowing. But once you have AI brains, robotic swarms, and self-healing supply chains, you can't just apply them to a single building.
No, the scale demands more. You apply them to the ultimate infrastructure.
The city itself.
Exactly. This brings us to Chapter 9, the self-building city, and Chapter 11, the thousand-day nation.
Treating the entire city as an infrastructure platform, this is where it gets really societal.
The most fascinating mechanism here is the concept of machine-readable regulations and AI zoning.
Dynamic AI zoning that dynamically adapts to population shifts. Because currently, urban development is bottlenecked by an incredibly archaic manual interpretation of zoning laws.
Developers spend years arguing with municipal planners over textual ambiguities.
But if you codify those regulations, translating the dense legal text into executable algorithms, the city's regulatory framework functions as an API.
An application programming interface, exactly. When an architectural firm completes a digital twin of a proposed megaproject, they don't submit PDF blueprints to a zoning board.
They push the massive 3D dataset through the city's API, and it performs compliance verification in seconds rather than by a bureaucracy in months.
Which is what Pagat calls instant permitting.
Instant permitting.
Yeah.
But here's where it gets really interesting.
Okay, let's hear it.
If a city becomes an API, does the role of the human politician or city planner disappear? Are we circumventing the democratic process?
This raises an important question, and it's a common fear. But Bagat clarifies that AI doesn't replace human values or public accountability.
It just accelerates the mechanics of review.
Exactly. Humans still set the ethical and strategic goals. The community, the planners, the elected officials, they decide the required ratio of affordable housing, the carbon emission ceilings.
The AI just ensures compliance instantly.
Right. It separates the legislative what from the administrative how.
And currently, infrastructure is reactive. We wait for traffic to get bad to build a road.
But the self-building city is anticipatory. It prepares for growth before the bottleneck emerges.
And we can scale this up to the thousand-day nation, a whole country running a national construction operating system.
Integrating digital land records with real-time finance. The economic leverage generated by that velocity is almost incalculable.
It forces a global arms race in infrastructure velocity. I marvel at the idea of a self-building nation. But the text notes there is an environment even more demanding than Earth.
Yes, an environment that will act as the ultimate pressure cooker for these technologies.
Space. Theme 8. Beyond Earth. Chapter 10. Infrastructure beyond Earth. We're talking about applying these concepts to lunar and Martian settlements.
The economics of space are brutal. Extreme constraints, high costs, and vast distance. Traditional construction is impossible.
You can't launch a prefabricated hospital to Mars.
No, the payload mass restrictions mean you cannot launch heavy machinery or traditional habitats. And the operational latency up to 20 minutes of communication delay between Earth and Mars means remote human piloting is impossible.
Which necessitates absolute autonomy. And this represents a total inversion of history.
Exactly. For thousands of years, humans arrived first and infrastructure followed.
The pioneers landed and then built the fort.
Right. But in space, infrastructure arrives first and humans follow.
The autonomous swarms land years in advance, and they use in-situ resource utilization, right?
Yes, ISRU, meaning they use what's already there, they prospect for subsurface ice, and they use microwave sintering to fuse the ambient Martian dust, the regolith, into radiation-shielded structures.
Printing habitats from lunar dust. It's like arriving at a hotel on a deserted island, but the hotel built itself out of the island's sand before your plane even landed.
That is exactly what it is. The vivid imagery in the source is stunning. Autonomous robots arriving on Mars years before astronauts to deploy power systems, mine materials, and print habitats.
So the astronauts arrive to a fully functioning colony.
And the innovations forged in the harshness of space will inevitably return to Earth.
The boomerang effect.
Exactly. The mastery of regolith 3D printing and swarm intelligence will lead us to the ultimate, permanent state of human infrastructure.
Which brings us to our final theme, concluding the textual analysis with Chapter 12, the century of continuous construction.
This challenges the ancient paradigm that construction is an event with a start and an end.
Right, there's a groundbreaking, a ribbon cutting, and then it's done.
But God argues that concept is dead. We need to introduce infrastructure that behaves like cloud software updates.
Oh, I love that, like how your phone updates its OS overnight.
Exactly. Bridges that monitor their own stress and dispatch climbing robots to repair micro cracks.
Roads that self-heal?
Yes, the data center that never finishes expanding. It just continuously grows like a living organism, integrating new server racks and optimizing power routing constantly.
This is so relevant. Listeners, think about your daily commute. Instead of waiting 10 years for a massive, disruptive road expansion, the city is just quietly, continuously upgrading itself around you in real time.
Autonomous microswarms surfacing in the dead of night to repave degrading asphalt before it becomes a pothole.
And citing the infographics continuous commissioning section, systems are tested and optimized continuously, not just at the end. The quote is, "The future isn't built, it's orchestrated."
It's the final unbinding of human potential from the friction of the physical world.
What a massive journey we've taken today. We've gone from realizing delays are just information bottlenecks to modular factories eating construction,
To AI digital twins running millions of scenarios.
robotic swarms communicating like bees, instant permits through city APIs, and Martian colonies built by autonomous 3D printers.
It really is a complete paradigm shift.
It is. But before we sign off, I want to leave you with a brand new provocative thought. Something not explicitly covered in the text, but that this entire discussion points toward.
Oh, I'm curious.
If our cities and infrastructure are constantly tearing themselves down and rebuilding themselves in real time based on AI efficiency algorithms,
Yeah.
what happens to our sense of history?
Wow. Yeah, the cultural memory.
Exactly. Architecture is how we remember who we were. If a city behaves like a constantly updating software program, relentlessly prioritizing flow and efficiency, do we risk losing the permanent, physical layers of culture that make a city human?
That is a profound tension. Optimization versus permanence.
Right. How do we program nostalgia or heritage into a swarm of 100,000 autonomous robots? It's something we're going to have to figure out.
Absolutely.
Thank you for joining us on this deep dive. We hope it encourages you to look at the construction sites in your own town a little differently. Maybe they won't be there for quite as long in the future. Thanks for listening, and we'll see you next time.